This presentation will be an introduction to the celestial coordinate system, and this is about the equivalent of latitude and longitude, but projected out onto the stars. A few things that are going to be different. When we think about latitude and longitude, we're usually imagining looking down on the Earth. For the celestial coordinate system, we're going to imagine that we're on the Earth and we're looking outward into space. And so that's where we're projecting this coordinate system onto. And we'll see how it happens to work out. The first coordinate, the easiest one to understand, is called declination. And it's how far above or below the celestial equator something happens to be. Now, the celestial equator is the place in space. If we took a straight line above the Earth's equator at every point on it, remember it's a circle that wraps all the way around the Earth, take a straight line from that all the way out to the stars, and for this, we kind of pretend they're all at the same distance, and it won't matter much from our viewpoint because we're always kind of stuck on the Earth. But we'll imagine that the celestial sphere is this giant sphere and the stars are kind of stuck on the inside of that thing. And so the celestial equator is the dividing line. It's going to have a declination of 0 degrees, just like the Earth's equator has a latitude of 0 degrees. And we just project that outward in every direction from the Earth's equator. The North Celestial Pole has a declination of plus 90 degrees. That's the angle between the equator and the North Celestial Pole. North Celestial Pole is the point in space directly above the Earth's North Pole. And then the South Celestial Pole has a declination of minus 90 degrees. This is kind of a northocentric viewpoint. The north parts get the plus signs. And then stars between the celestial equator and the North Celestial Pole have declinations between 0 degrees and 90 degrees. And if we go past the North Pole, we start ticking down from plus 90 degrees. You'd pick the closest equator to you rather than leaning over backwards, or closest equator to a point in space. And stars between the celestial equator and the South Celestial Pole have declinations between 0 degrees and minus 90 degrees. Okay, here's a little view of the Earth looking at it from a ways away. You can see the Earth's equator on there. I've got an arrow drawn to where Moses Lake is on the Earth approximately, and the North Pole's up there. I've drawn some arrows going from the center of the Earth through the equator out to infinity, and that'd be in one direction, and then from the center of the Earth through the North Pole straight up. So which arrow points to the celestial equator? Let you think about this for a few seconds. And it would be arrow 1, because from a point on the equator directly overhead, arrow 1 would point to that. But is there another arrow that points to the celestial equator? Think about that. You might pause this and ponder it. It's arrow 2. It also points to the celestial equator. How can that be? Well, remember how far away the stars are. With the Earth as something about the size of a fly speck in a classroom in Big Bend, the next nearest star is going to be in El Paso, Texas, or that far away, and a point between that little tiny dot on the ceiling and its equator, you draw arrows to something as far away as El Paso, Texas, and those arrows are going to be parallel, pointing in that direction. So any arrow from Earth that points parallel to arrow 1 is also going to be pointing to the celestial equator. same viewpoint again. We know that arrows 1 and 2 will point to the celestial equator. Which ones point to the North Celestial Pole? I'll pause for just a few seconds. You can pause this and think about it if you want. Well, arrow 4 for sure points to the North Celestial Pole because it goes from the North Pole straight up for an observer there, but so does arrow 3. Okay, it's the direction from Moses Lake to the North Celestial Pole. It is not straight overhead. It's a ways down from straight overhead. Another viewpoint here. Which arrow would point to the southern horizon for an observer in Moses Lake? Now remember, an observer in Moses Lake cannot see the curvature of the Earth. Their southern horizon is actually determined by this little 2-meter high person standing on a sphere that has a radius of 6,370,000 meters, and compared to that huge sphere, a 2-meter person is not very big. And so our southern horizon is going to be arrow 1 on here. How about our northern horizon? That will be arrow 5. On this diagram, arrows 1 and 7 will point to, arrow 1 will point to our southern horizon, arrow 7 will point to our northern horizon. Now, what about the zenith? Which arrow points to the zenith for an observer there on the Earth's equator? The zenith is the point directly overhead, and it depends on where you are on the Earth. But arrow 2, for an observer there on the Earth's equator, arrow 2 will point to their zenith, straight up from them. Which arrow points to the zenith for an observer right there in Moses Lake? It will be arrow 4. That's straight overhead. We could ask more questions here. Arrow 3 points to the celestial equator for an observer in Moses Lake. If I look on here, I don't know if I can draw on this or not. Maybe I can. I'll draw with red ink. Something you can see here is this angle down here is equal to 47 degrees. This angle up here would also be 47 degrees. I can't draw very well with a mouse, but you can kind of see it. Now, since this points to the celestial equator, that's pointing to a point in space that's 0 degrees. That means our zenith is 47 degrees up from 0 degrees. This direction is to 47 degrees declination. I didn't draw that very well, but that's something else we can dig out of here. Okay, let's see if we can put on a number on the stars that are always above our horizon. Okay. Now, this is that picture that was in an earlier video you probably watched. This is taken from Hawaii and it's looking north. This little star track right here is the track of Polaris on that diagram, and the center of all these tracks is the North Celestial Pole. I'll kind of make a big dot for it. We'll see if we can put a number on these things. Whoops, coming down here to the horizon. Anyway, that would be the direction north on Earth. But something you can see on this thing is that some of the star tracks on here, if you could complete the circles for them, they would never touch the horizon. Okay, now this is a picture taken from Hawaii, so it's going to be a bit different. In fact, from our latitude, you would raise the height of the center of this circle by, let's see, Hawaii is 21 degrees latitude, so you'd raise it up by 26 degrees because we're about 46 degrees north, 47 degrees north latitude. We are about 26 degrees of latitude north of Hawaii, and so we'd raise it up quite a bit. But wherever your latitude happens to be, if you complete these circles, anything within that circle that doesn't touch the northern horizon is always going to be above your horizon. So let's put a number on it for Moses Lake. Here we are at 47 degrees north latitude, 0 degrees declination here, 90 degrees declination up there. Okay, our zenith is up in that direction. Our northern horizon is over here. What's the declination of our zenith? Well, I kind of did that for you a little bit earlier. This angle down here is 47 degrees. This angle here is also 47 degrees. Sloppy handwriting with a mouse, but that's okay. And that makes our zenith up there 47 degrees above the North Celestial Pole. Now, that's only for Moses Lake, or points with our same latitude. If you move north or south from there, it's going to be different. But it so happens that the declination of our zenith is the same as our latitude. And that's the same for every point on Earth. If you're on the equator, your zenith, points in the direction of 0 degrees declination, because your zenith is pointing at the celestial equator. That's 0 degrees latitude. If you go to the North Pole, your zenith is directly overhead. That's pointing at the North Celestial Pole, which has plus 90 degrees latitude. What's the declination of the northern horizon at Moses Lake? We have to do a little bit of math, but the way I can figure it out is I know that this angle right here is 47 degrees, but this is a right angle here, and this angle plus this one have to add up to 90 degrees, and if this one's 47, that makes this one 43, because 43 plus 47 is 90 degrees. Well, here's another right angle. It's this angle right here. Not very well drawn. And if one of them's 43, then the other one's going to be 47. Okay. However, that 47 is below 90 degrees declination, so if I take 90 degrees and subtract 47 degrees from it, I get the declination of our northern horizon. It's going to be 43 degrees. So northern horizon, I'll just write it down here. I'll wish that I could erase it pretty soon here, but maybe not. That's the declination of our northern horizon at Moses Lake. Stars above the northern horizon are visible. Those below it are not. Things in this direction at this instant would be above our northern horizon. Stuff that's on this side of it are below it, so we can't see those things. So there's our northern horizon again. And actually, at this instant, the things that are above our horizon, here's our southern horizon, the stuff that's above our horizon is everything in this region here is above it. So we've got that labeled. Anyway, that region is above our horizon at this instant. Now, let's have the Earth rotate by 12 hours. There's our northern horizon now. And the stars in that region between those two arrows stayed above the horizon the entire time. And remember what the declination of that thing was? This was 43 degrees north latitude. 12 hours later, this will have a declination of 43 degrees, plus 43 degrees, and the things above plus 43 degrees were always above the horizon. So that's pretty good. Any star with a declination above plus 43 degrees is always above our horizon. Which ones are never above our horizon? Let's see if we can figure those out. We're not going to get it from a picture like this because it's not that easy to figure out which ones are never above it, but we can do it from those diagrams we were just looking at. And if we go back to this one, here we've got 0 degrees declination. Remember, this angle was 47 degrees. If that's 47 degrees, then this right angle here, lousily drawn right angle. Let's see if I can do better. That's only slightly better. But anyway, that's a right angle. This one has to be 43 degrees in order to add up to 90 degrees. And in this direction is going to be minus 43 degrees. Man, I'm good at this. I think I'm getting worse as this thing goes along. But anyway, minus 43 degrees there. Again, we'll work off what's the declination of our zenith at Moses Lake, 47 degrees. And then what's the declination of the southern horizon? It's minus 43 degrees. And stars above the southern horizon are visible. Those below it are not. And above is the stuff toward the north celestial pole. So the stuff that's above the horizon is in this direction. Okay, 12 hours later, here's our southern horizon again. Now remember, this had a declination of minus 43 degrees. Okay. That's not going to change as the Earth spins on its axis. So over here, this arrow will also point to minus 43 degrees. And the stars in that region remained below the horizon the entire time. Well, it's kind of nice that that's minus 43 degrees. From our latitude, we can always see the stars north of plus 43 degrees, and we can never see the stars below minus or south of minus 43 degrees. And that 43 happens to be 90 minus our latitude. Summing it all up, stars up there are above our horizon at all times of day or night. Those are the ones that if we take a time exposure picture looking north, they travel in complete circles and don't touch the horizon. And stars down there are below our horizon at all times. Those are the ones south of minus 43 degrees. And in between the two, they rise and set every day of the year. And we're going to learn about that. I'm going to have you do an activity with Stellarium, if you haven't already, where we'll investigate those things. Okay, put numbers on them. What number can be used to describe the stars that are always visible? I'm going to fly past these, but you could pause it and think about that. What number can be used to describe the stars that are never visible? Which of the following stars are always above our horizon? I'll let you think about that. See if you can figure it out. Which of the stars is closest to Polaris, and which is farthest from Polaris? For practical purposes, you can just say the declination of Polaris is plus 90 degrees. And it's actually about 89.3 degrees, but that's pretty close to plus 90 degrees. And so you can work with those. Can we see stars which are south of the celestial equator? Yes, we can. Anything down to a certain number we can see. Anything with a negative declination we can see at least some part of a 24-hour period, or we could if the sun's turned off anyway. Some time of the year we'll be able to. Some of these stars with negative declinations, Rigel, that's up in the evening sky right now. Sirius is up in the evening sky right now. Those have negative declinations. Rigel is one of the bright stars in Orion. Sirius is the brightest star in the night sky. Declination of minus 16. Whoops, I've got things labeled wrong here. This should say declination, not right ascension. I don't know what I was thinking. Right in declination on that. Okay, this is one of the luckier pictures I ever took. I think I took this in 2015. We'd gone to Hawaii and stayed in Hilo. We'd heard that the volcano there at Volcanoes National Park was kind of erupting, or at least glowing at night, and so you could go out and see it. And went out there and set up a camera on a tripod aimed toward, I think this is Kilauea Crater. I'm not positive. I get my craters mixed up in Hawaii. Took some time exposure pictures of 20 or 30 seconds to try and get some that worked out pretty well. But there are things in this picture that you cannot see from Moses Lake. They have negative declinations that are greater than minus 43 degrees. That means it's a number like minus 50 degrees or minus 60 degrees or minus 70, something like that. So we've got a couple of tourists from Moses Lake visiting Hawaii, and they happen to go out here and look at that. And the husband says, "Now there's something you don't see in Moses Lake, Martha." And Martha says, "You can say that again, George. Just look at that. Alpha and Beta Centauri with declinations of right around minus 61 degrees. We can never see those in Moses Lake." And I was actually thrilled to see those two stars in Hawaii. By the way, these are Alpha and Beta Centauri. Alpha Centauri is part of a multi-star system, and it is the closest star system to our own sun. There's a star in that system called Proxima Centauri, which can't be seen with the naked eye, but it's the closest star to the sun. And George says, I meant the volcano. Well, they're both kind of thrilling, but I got a big kick out of being able to see Alpha Centauri for the first time in my life. Okay, here's an interesting picture. The part that's in the top half of the picture is the actual stars. The part that's in the bottom half of the picture is a reflection in a lake. And I think this was taken somewhere in the Andes, but I don't remember where. If I tracked it down on the astronomy picture of the day, I could find out. Do you see anything you recognize there? How about an upside down Big Dipper? Now, something that we haven't learned yet, or I haven't shown you, some of you may know this, is that if you find the bowl of the Big Dipper, this is the handle of the Big Dipper, and then here's the bowl. Big Dipper. These two stars here, this star is called Dubhe, and this one's called Merak. They happen to be pointer stars. They point toward the North Celestial Pole. To get to them, you go in this direction about 30 degrees from the bowl of the Big Dipper. You get to the North Celestial Pole. Well, for us, the North Celestial Pole is always above our horizon. But as you go farther and farther south, that North Celestial Pole gets closer and closer to the northern horizon until when you get to the equator, the North Celestial Pole actually lies right on your northern horizon when you get to the Earth's equator. And you can't really see it because you lose it in the haze of stuff close to the horizon. For someone at this location, when they see the Big Dipper in the sky, the pointer stars are pointing below the horizon. That means the North Celestial Pole is below the horizon for these viewers. and that means you're in the southern hemisphere. Where's Polaris? It's down here somewhere at the tip of the arrow, but you'd have to be able to look through the Earth to see that. So it's below your horizon. You're south of the equator.